Okay. I think this lecture makes more sense if we start by looking at the calendar. So let's get that up. Let's see. No one looks at that one, right? Yeah. Oh no. Oh, it's on room computer. Okay. So, I think I probably have been like less invested on selling you on this class as I was last term when it was the Bitcoin class. But there is a motivating end-to-end semester project that's been going on. It's perhaps beneath our notice this entire time. And that's building up to you implementing a version control system, which is like Git, right? And implementing version control systems are interesting because you like look at files and you see if there's differences between them and you sign the changes and stuff. So it's all the stuff we've been doing. We're now sort of getting past the first midterm, getting to the parts where like the hard thing is there now. And the hard thing is basically public-private keys. I'm going to teach a new version of public-private keys. I actually don't know this. I'm going to learn it by making the slides. I've started looking at the slides. There's this new thing. It's variously called ECDSA or ED25519. I don't actually know what it was going to be called. I was supposed to have a guest speaker that was going to explain this stuff to all this, and that person's like not showing up, and I was like, I can teach it, right? So I'm stepping a little bit outside of my comfort zone for like 1 or 2 weeks this term. I'm trying the new cryptographic system. And I like RSA better, which is like the old one people don't use anymore. So I didn't want to learn this new one, but you need to know it. So I'll do that next week. It actually looks pretty interesting and not that different. But these public-private keys, they use big numbers. So usually when we did RSA last term, it was you needed a 4096-bit integer type. Actually, that's not true. You needed to be able to work in up to 8196 because you needed to be able to multiply 4096s by each other. So you needed huge integers. And some of you may have noticed, like, oh, Python has huge integers in it, and Python's written in C, so probably someone wrote how to deal with big integers in these languages. And it's true, someone did. Someone also wrote how to deal with floats, right? And did I let you use that? No, absolutely not. I made you write your own. So I'm going to make you implement your own infinite precision integer library. And you're going to have fun while doing this, when you're doing addition and when you're doing subtraction. And then when you're doing multiplication, you're going to be like, this seems kind of hard. And then you're going to get to division and you're going to be like, has anyone ever done this successfully ever? And I know someone has because the code exists. But I worked on this for like a month last year, and there's still one bug in my code in the case where there's a large number of zeros between two non-zero things. And of course, this occurs at probability like literally 1 over 256, like 2 to 256. Like it's like ludicrously unlikely for this bug to occur in my code. Well, I can't actually figure out how to fix it in C. I know how to fix it in Rust, because what I'm actually doing is I need a nullable integer type, which we now have. So it might be easier in Rust. Anyways, implementing division over arbitrary precision integers is just this like brutally hard thing to do. So I'm going to make you do that. But I'm nice. Remember? Do we all remember that I'm nice? You will attempt, but you're allowed to call it a challenge problem. So I'm going to make you do it, but you can think of it as a challenge problem while you're working on it, right? So that I'm nice, right? Okay. Then once we have the big integers, then we're going to try and implement the crypto system over the integers. Then what's going to happen? Your code is going to be slow, it doesn't even function. And that's okay. Because then you're going to learn one other thing, which is that, not only does it matter like that this is possible, but there's also correct, or I don't know, you'll do it a correct way, right? But there's higher performance ways to do this, and this might be one of the first things where you like try and do something at your computer that you know can do quite quickly because you can just type the commands into the command line, and then you can write the code that does the same thing and it will never finish. I think last class I calculated that like my code would finish running in like 2,000 years or something, right? Okay, so that's what we're working on, right? Okay, there's one other thing, and it's going to be a little less sneaky this term because of how memory is managed in Rust. But there's one other thing that's going on here, which is that the way you implement addition, subtraction, multiplication, and division is solving the same problem that people that design hardware are trying to solve. Why is that? Well, inside a computer, there are transistors that hold single bits, as we discussed in the bits lecture and in the Hamming lab and all of these things, right? What I'm going to ask you to do now is I'm going to say, like, hey, you've got those integers. Now I need you to add something together that doesn't fit within a single integer. That is actually the same problem as adding things together that don't fit in the same bit. So you're actually solving, the same time you're solving the software problem of an infinite precision integer library, you're solving the hardware problem of how do I implement arithmetic using bits. So you're going to learn two things at the same time. So a good bit of number theory, and you're also going to be learning computer architecture, and you might not know it, but you are. That's why this is the best assignment in the universe. That's why I convinced myself to teach this way. Now, I don't know if this is actually a good idea or not, and I just think it's really cool, but I want you all to know that I think it's really cool, okay? So that's what we're going to work on today. And in order to work on that, I'm going to talk about numbers for 90 minutes, now 82. And then at the end of those 82 minutes, you'll probably be fine. Like, numbers aren't that complicated, right? So let's go ahead and do that. Let's do some numbers. It's already open. It was already open. The thing was already open. Am I actually recording this? That is very small. Look how tiny it is. It's little. Okay. Okay. Oh, the midterms verbal update. Okay. So here's the update on midterms. I am frustrated with the first years, so I'm waiting till I'm not mad, and then I'm going to look at your midterms. In my CC class, I just had them grade their own work, and a student that didn't turn it in self-graded as a C, which I don't know how that works, right? So I'm going to, have a little coffee and calm down, and then I will look at your midterms, right? Because your midterms looked fine when I started looking at them, and now, I'm only seeing red. Okay, so, anyways, if you see a first year, I'd assume they're going through it too, so you should be nice to them, okay? Okay, I'm just going to ask one thing, right? All of you have, always turned in a midterm if you've had a midterm assignment, right? Okay. I don't think I've ever not turned in a midterm assignment. Okay. So this is typical? Okay. I'm wondering if I should have been more specific that you have to turn in the midterm. Okay. That's the midterms verbal update. You're ready to start the next assignment whenever. It's pretty cool. I do think it will actually be possible to do division in Rust. I think it was basically impossible in C. Mine, I think, was the closest last year, and we had some people that really liked programming that did not get it last year as well. So it was one of two assignments I gave last year that we think might be impossible. Okay, but I haven't assigned you anything impossible yet, have I? Right? Notice that this is coming right after me complaining about the students doing the midterms, right? What if I gave an impossible midterm, right? We don't know. Okay, so today I'm going to introduce what I think, and, okay, some of you in here might be math majors. Are there any math majors in here? I might be safe this year. There were a couple of them, and I don't know how well you all know math majors, but they, sit in the front row, and they ask questions. And it's I don't know math. Right, I'm trying to explain computer science, and I just have to use words to do it, right? So I say the word set from time to time. They're that one's actually a group, and I was I don't know what that word means, right? So, anyways, I'm going to talk a little bit today about the concepts that I think are finite sets and rings. Do not ask me what a ring is, because if you ask me what a ring is, I'm going to press Control-T, look it up on Wikipedia, and read the definition to you, right? That's how I know what a ring is, right? We're going to introduce arbitrary or high-precision integers. Why do we say arbitrary and not infinite? Well, there are, of course, still integers I can't put in my computer, but they can be much, much larger than 128 or 64-bit integers, right? So the entire integer range up to several thousand bits will work just fine. After that, your computer will slow to a crawl, but still be able to proceed. Do not try and find a prime number that has 1,000 digits in it. There's just, like, that's a research problem, right? I'm going to go over the arithmetic operations, specifically addition, subtraction, and multiplication. Addition and subtraction are the same thing. And it's the very unusual case where addition and subtraction are the same thing, and multiplication and division are as different as any two things. Like, multiplication is much more similar to addition and subtraction than it is to division. Then I'm going to talk a little bit about function types, and this little bit about function types is teasing this sort of computer architecture idea that's been floating around underneath all of this. Okay, so finite, sets, and rings. Okay. There are these people, they walk amongst us, they're called philosophers. There was a philosophy major last time I took this class that was very stressful. And I think there's this idea called finitism, which is that there's a finite number of things. So one classic example of this is that I think there is one electron. That electron is simply going forward and backward through time, and so that's how we perceive that there's more than one, but it's all the same electron, right? So I only believe there's one subatomic particle, right? Now that's a weird thing to believe, but that's finitism, right? And then some finitists are very extreme, and some of them don't believe in numbers larger than 2. I am one of these finitists, right? Because I've never seen 2 of anything, right? Sometimes you're like, that. Oh, there's 2 leaves. I was like, no, those are completely different leaves. That's one of this leaf and one of that leaf, right? What are you talking about, right? And then people always try and get me. They're like, but if I look at the periodic table of the elements, every hydrogen element is exactly the same. It has 1 proton and 1 electron in it. And I say, yes, but that's the same electron and same proton in all of the hydrogen atoms. And then they get really mad, right? But I don't believe in numbers larger than 2. The only numbers I believe in are 0 and 1, okay? Which makes me very, very good for being a computer scientist, right? Because computers also only believe in 0 and 1, right? Now, what I do believe in is I think I can take a vector of zeros and ones. That seems fine to me. That's allowed. Because I already know that that electron that's in my transistor that's causing it to either be a 0 or 1, I can use that electron as many times as I want. All right, so I can have as many zeros and ones as I want. And I can simulate there being larger numbers. The larger numbers don't actually exist, but I can pretend they do. Right? And so the same way I can't write down an infinite number of zeros, I can write down numbers larger than 2, even though they don't actually exist. And that's the problem we're solving. So I'm going to refer to the integers and the nats at various times today, and so I'm introducing these symbols. I suspect you may have seen these symbols before, but I don't know. So I'm going to denote the integers as the mathematical symbol Z, and so that is LaTeX Math BB, which is like, I don't know what BB stands for, Z. My understanding is Z is the first letter of the word integer in German, and that's where we got it. I'm also going to talk a little bit about the natural numbers. The natural numbers are not the whole numbers or the round numbers, right? These are the counting numbers. I've heard different definitions of the natural numbers, but one of them is any number that can refer to the number of elements in a set. And the question is, does that contain 0 or not? Because is the null set a classical set, right? So we denote those n. These things look a lot like the integers and the unsigned integers in your favorite programming language, but they are not the same, and it is important how they are not the same. We can model them, even though we can't actually use them. So there is a way to refer to the natural numbers in Python with iter tools, and I'll just go ahead and demonstrate this because it's fun to do so. That's really small, isn't it? Oh, I don't remember how import statements work. So I can look at this thing called count, and it contains the natural numbers, and I could say, for example, for I and n, print I, and this will print for a long time. This will actually print forever. And But this is maybe not necessarily the most productive way to do this. Nevertheless, we can do that forever, and we can also do things like, I don't know, whatever you want. I mean, here's an example. What I'm going to show here is that given the natural numbers, you can construct the integers, which is a potentially useful thing to do. I think this might be called a diagonalization, but I don't remember for sure. So we've got the natural numbers, which look like this. I'm actually going to restart them by saying n equals count. Let's chop both of these in half. Okay. Now, one of the things that you do when you're introducing the numbers and talking about them is you make different types of numbers out of other different types of numbers. So I'm going to make the integers out of the naturals. I can do this because even though there are things that are in the integers that are not in the naturals, most prominently -1, there are not more numbers in the integers than the naturals because there's an infinite number of both of them. So I'm going to take every one of the infinite numbers in the naturals, and I'm going to make it correspond to one of the infinite numbers in the integers, and I'm going to make sure that I never run out of them. Now, the obvious thing to do to many people is, oh, I will just keep counting in the naturals until I get to all of the positive integers, and then I will start with the negatives. You can't do that because there's an infinite number of positive integers, right? So you run out. So what we actually have to do is we have to start at 0 and build out in both directions. So how am I going to do that? Well, one of the ways to do that is say, I'm going to do little n. It's going to equal 0, 1. It's going to equal list range 10. Okay. So if I take all of these and I want to make sure that I'm getting all of the integers, something I can do is I can sort of just alternate over them. So we can say, for example, is n divisible by 2 for, I don't know, I and n. And I think I have to call this one I. And so this is a way to take every other value in the naturals and only look at every other one of them. And once I'm doing that, well, I can say, well, oh, this can actually be the sign. So what I can do is I can raise -1 to this power, and then I can multiply that by I divided by 2. That didn't work for some reason, probably because I don't know how math works. What is I percent 2? Am I doing something silly? I have 2 1s and 2 2s, so I'm very close to what I want, but I'm not getting the sign flip I want. Is it to the power? -1 if else 1. There we go. So I don't know what I did there. Wait. Oh, it's not multiplying. Okay, hold on. I think I have to do parens. Okay, here we go. So, what have I done here? I've used, is there a word for like numbers being odd or even, like parity or something? So I've checked to see if values are odd or even for all of the values in my subset of the natural numbers. If the value is odd, I set it to be negative, and if it's even, I set it to be positive. So -1 if odd, else 1. Then I multiply that by the floor division of the value itself, so that I'm going to output 2 of each instance of the natural numbers for every instance of the natural numbers there are. So 0 will correspond to 0, but both 1 and 2 will correspond to 1. 3 and 4 will correspond to 2. 5 and 6 will correspond to 3. Right? So I've doubled my instance of each natural number by dividing by 2. And I have an infinite number of them, so I can do this. And then I alternate, and I get all of the positives and the negatives. So I can take this same operation. I'm going to change the outer, in wrapping things, to parens. And the reason I'm going to do that is because If I did not do that, I would have to evaluate this expression over an infinite number of values, which would take an infinite amount of time. With this generator expression, I'm just creating something that I can ask for the next value every time. So I can go ahead and create that. That is z, the natural numbers, or the integers. And then for I in z, we can look at z, or we can look at I. And this is going to give me all of the positive and negative values that exist. And it will take some amount of time to do that. In fact, it will take an infinite amount of time to do that. But it will eventually get to all of them. We'll see that I am not skipping any values here. And that is how we can go back and forth between having the integers and the natural numbers. Now, this is the mathematical way to do this. This is not the way it is done in computer hardware, but it is a completely valid way to do this thing. The reason I've shown this to you is that in many computer science programs, we talk about countability and uncountability of sets and infinite sets, and it's the component of a very important proof that shows that not everything is computable. Not everything can be solved by a computer. This is a step in the proof that shows that, and so I wanted to show it to you, even though I'm not going to show you the whole proof, so you can start thinking about these things as we start thinking about using our potentially infinite numbers. Okay. I believe I have protected myself from math majors this term, so I think there are none here. So I am going to say something that is potentially controversial. For the sake of this class, I am classifying 0 within the natural numbers. There is a literal paper and research line, at least beginning in 1977, discussing whether or not 0 is a natural number. I'm just saying when I refer to the natural numbers this term, I am always assuming 0 is in there. And the reason I'm doing that is because they're in there in Python. And if I weren't using Python, I would be using Haskell, which has the same thing. All of the Python in this class could have been Haskell and would be Haskell if I thought you knew Haskell. I wasn't going to teach you Haskell and then also teach you Rust. That seemed reasonable. Here is my claim. My claim is that the natural numbers are akin. I'm not defining the is akin to relation. I just had to have some way of expressing this idea. I'm saying they are akin to unsigned values for some size little italics n. So they're similar. At small finite values, they have the same properties. The natural numbers probably look a lot like the unsigned integers. That's one way to say this. There's one real problem that is not related to the reals. I just wanted to put the little, the real numbers like pi and e, those ones. And the problem with this is even the unsigned integers are not present in Rust or any other computing language, right? They're nominally present in Python, right? And so even though the unsigned integers and the natural numbers look a lot like each other, we can't actually use them for the same things. And an easy way to do this is to just pick an arbitrary natural number. And in fact, if you randomly select a natural number, you can do this. And also we have to do is we have to check to see if that natural number is contained within the set of the natural numbers in Python, right? And so I arbitrarily selected what I thought to be a fairly reasonably sized number, which is a googolplex. So this is a very small number. It is a finite number. It is smaller than an infinite number of values, and it is larger than only a finite number of values. So the probability of selecting a number this small is 0%. This is smaller than any number I could randomly select. And I'm going to check to see if I can find that natural number in Python. So how are we going to do this? Well, let's get back out of full screen mode. And I don't know if I've shown this to you before, but this is one of my favorite ways of using Python because I use it often this way. I use the C flag to evaluate text directly at the command line, and then I write my Python code inside quotes, so I can print anything I want. Now, the first mistake that I cannot make is I cannot use the same quotes inside of the Python script as I do to enclose the Python script. And in fact, this is why Python allows both types of quotes. So I'll use single quotes and I'll say hi world. And I didn't close the quotes. There we go. There's hi world. Okay. And so using this same technique, I don't want to do that. Okay, using this same technique, we can check to see if numbers are contained within the natural numbers. So for example, we can do Python 3 command. I am going to import count from itertools, import. I'm just going to do star because it's less typing. I'm going to line break with a semicolon. The same way I can line break with semicolons in Rust, it is also allowed in Python. Big Python doesn't want you to know that you can write all of your Python code in a single line, but you can and you should, okay? Do not tell Professor Cordova I said you should write all of your Python code in a single line. Apparently this stresses him out. Okay, and we're just going to check to see if 0 is in count. There we go. I think that's fine. And it is true that 0 is in count, but we already knew that, right? So what are we actually trying to do here? Well, we want to see if some larger numbers are in count. And we started with, for example, I think this is a Google. Oh, that's not. That's 1,000. How do you... Exponentiation is double asterisk in Python, right? That looks right. Oh! Oh, no. Oh, no. My computer's finding out it can't actually deal with numbers. I think that someday this will return, and we should figure out how long it's going to take. But remember, this isn't even Googleplex. This is just a Google, right? So this is much, much smaller than the number I was going to look at. I'm going to turn this off before I turn my computer into a heater. There we go. And so what can we do here? Well, we can time how long this takes, and we can make projections of how long it's going to take Python to evaluate a numerical expression. So I'm going to time. Nope, I'm not. I pressed some buttons that I didn't mean to press. So we can check this. I'm going to see how long this takes. So I'm going to prefix the command with time. And on this device, it is 0.31 seconds. I generated these slides on my desktop. It is unsurprising a desktop computer is about twice as fast as a laptop. I think that's pretty typical. So this is how long things took. And if I run it multiple times, I'm getting pretty close to the same speed, right? Nothing is too interesting here going on. You can think of this as various operations taking a certain amount of time. The way I think of it as is, especially for this operation, mostly what I'm timing is how long it takes for Python to turn on and go find itertools. That's really what it's doing. And I think we're probably a little bit faster, but we're not. So itertools is free, apparently. It takes no time at all to find itertools. It just takes a certain amount of time to do anything with Python. So I'm guessing then maybe the time is the time it takes to take those strings and turn them into some code and run the code and turn that code back into strings. I don't know what it's taking all that time on, but it's probably something like that. So we can check different values here. And I think previously I checked it 1,000, so we can check 1,000 again. That takes the same amount of time. So I guess it doesn't take any time at all to check arbitrarily large numbers to see if they're within the natural numbers, right? But one thing I can do, of course, is I can write a loop. And here's this an example of a loop here, right? We can loop over this, and we can see if there's like any point at which this starts slowing down. So how did I structure this here? There it is. So I can basically just put an n here. So some n value, right? And I can set it to, I don't know, 17. Oh, that's already not a very big number. Please come back. Okay. What about, so I think, is 10 to the 9th, that's a billion? It should be easy to count to a billion. There's that many people, right? We can just tell every person to think of a number. Oh, no. Oh, it's a disaster. Python can't even count the number of people that live in India or China, but it's fine for other countries, maybe. Well, is it? Okay. This isn't that many. Surely it can... Oh, can it not do that either? Okay. Can it do 5? Oh, that's fine. How about 6? Ah, and we see that somewhere it is starting to slow down. So at relatively small numbers, at 1 million, Python is already having a hard time checking to see if numbers are in the natural numbers, right? This is not good. Most numbers are bigger than 1 million. In fact, of the natural numbers, we can essentially say all of them are bigger than 1 million, right? And of the integers, we can say half of them are bigger than 1 million, right? So we're running out of numbers here pretty poorly. What I did is I timed this at home, and I got these results for the amount of time. But we can do this pretty easily here as well. Oh my gosh, I keep pressing things I don't mean to. We can throw a 7 in here real quick. And we see we appear to have discovered some form of exponential scaling, right? And so if I put an 8 in here, how long do I think it's going to take? Well, this is about 0.29, and that is about 0.6. So it seems like it costs you 5 times longer every time I add another digit. So I think this is going to take over a second, but it's probably much worse than that because it's probably exponential or something. Ooh, so it is 10 times longer. And 10 times longer makes much more sense because I'm looking at 10 times as many numbers. So what happens if I put 9 in here? I think it's going to take 30 seconds. And we'll let that run on the other screen. So what are the values I checked at home? And you can check at home as well. Well, I noticed that I had essentially instantaneous performance, and we can debate here, up to around 10,000, right? At 1 million, I started slowing down. And what's in between 10,000 and 1 million? I don't know. That seemed like an odd place for this to be breaking over for me. So 25 seconds, so it is going up slightly under a factor of 10 every time, right? I don't really know why it slowed down around here. I assumed it would slow down when I got to 32 bits and had to start looking at larger values. I thought it would slow down a lot there. But it's slowing down well before then, so we can't even check how much we slow down when we go over the 32-bit size. So I calculated this out, and I think it would take me 316 navenvigintillion years. I just asked Wolfram Alpha. I don't know what this number is. How long it would take to see if Googleplex is in count on my computer. Now, remember, this is on my desktop, so it's actually 6,000 navenvigintillion years on my laptop, which is much slower, right? Because you get to that first 316 navenvigintillion years, and you think you're done, right? But you have to turn around and go all the way back, right? And this is why Rust invented constants. It's very easy to simply say to your foolish programmers who keep asking if Googleplex is one of the natural numbers, yes, and go home. And why do you keep asking me these questions? Why are you typing something into your computer that has more digits than you can store in memory, right? And so Rust, in its infinite wisdom, said, unless you say otherwise, your integer is an I32. It's a signed 32-bit integer. Why they picked signed values, I do not know. I tried to get to them in time. Turns out this language, I think, is older than I am, and I'm older than dirt, so this is an old language. But they very helpfully say, not to worry, I have a plan. I'm just going to let everyone that uses the language know that if they put in a number bigger than that, I'm going to explode, right? And now my computer was still going to explode when I put in numbers larger than that, right? But it didn't have the decency to tell me in advance, right? I had to press the run button, and then my computer just went away, and I never saw it again. So you can read more about this or not at the hyperlink. I realized I'd been calling out all of my hyperlinks read more, and it sounded like a command. And I felt bad about that. I don't like to boss people around. So I have specified that I'm a hyperlink, not an imperative. Okay. The following, I think it's 3 slides, are going to be exact quotes from Rustbook. Why are they exact quotes from Rustbook? Because I think they're stupid and I don't agree with them. So I'm just going to tell you what the Rust people said, right? And you can make up your own mind about it. Now, when I was learning the Rust programming language this summer, when I got to this section, I took so much psychic damage, I had a complete meltdown in the CS Students Department Discord, and I said I wasn't going to teach this class in Rust. That's how much I hated this, right? And they told me that it would not come up in this class, right? The students that were trying to bamboozle me into teaching Rust. Now, those students took this class in C last term, which means they knew the contents of this lecture, which is expressly about triggering integer overflow, would come up. And so now I'm going to read you what the Rust book says about integer overflow, and it is the most unhinged thing you've ever heard about a programming language in your life. This is insane, okay? All right. Maybe you won't hate this, that's fine, but I hate it a lot. Okay. Let's say you have a variable of type U8 that can hold values between 0 and 255 inclusive. If you try to change the variable to a value outside that range, such as 256 decimal, integer overflow will occur, which can result in one of two behaviors. Wait, what do you mean one of two behaviors? I don't believe in numbers as large as 2, right? Okay, when you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic, and panic is Rust for give up, right? That causes your program to panic at runtime. Oh, okay. So the program will compile, and if it's in debug mode, it will compile with something in it that says crash. This is considered a good design by some people, right? It's like, oh, I can compile programs that crash. Thank you, Rust. I can do that without your help, right? Okay, so it's going to panic when you run it. Also, this means you can compile it once and crash it an arbitrary number of times, right? Because it will crash every single time you do this. Okay. Rust uses the term panicking when when a program exits with an error. Okay. So that was pretty bad, right? But that's actually only one of the two behaviors it has. Okay. The other behavior is what I refer to as the cool or based behavior. This is what the language should have done. And it shouldn't have told you it was done. You should have just found out. But it's actually going to tell me I'm not allowed to do this. Okay. When you're compiling in release mode, have any of you ever compiled in release mode? Yeah, okay, so not everyone's hand is up, right? Did I teach you about compiling in release mode? No, I didn't find it interesting, right? Or did I? Really?
You mentioned it.
I mentioned it.
Like when we were learning about Cargo.
Classic me, bringing up release mode. I do love release mode. We like Taylor Swift's newest release. I feel like the kids these days aren't into Taylor Swift anymore. That's a recession indicator. Okay. Rust does not include checks for integer overflow that cause panics with release mode. So what does this mean? This means you can compile your code in debug mode, test it, ensure that it never does anything unsafe because it always panics if it's going to do something unsafe, recompile it in release mode and release the code, and the behavior will have changed. There will be checks that are absent from... Okay. This seemed bad to me. I don't know. No one else seems to think this is bad. Okay. Instead, if overflow occurs, Rust performs 2's complement wrapping. What's that mean? It means modular arithmetic. We'll cover that in a minute. In short, values greater than the maximum value the type can hold wrap around to the minimum. In the case of a U8, the value 256 becomes 0, the value 257 becomes 1, and so on. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. And that's false. That's not true. I always expect it to wrap around. I was sure. I have spent so much time thinking about how finite these numbers are in computers. If I ever add 7 to 250, I always expect to get 1 back. And I am disappointed when that doesn't happen. And when I compile my Rust code with debug mode on, it panics. I don't want it to panic. I want to panic. Okay. Relying on integer overflows wrapping behavior is considered an error. And this is what really did me in, right? Because I rely on it all the time on purpose. And in Rust, you're supposed to use a method. Oh, methods, that's object-oriented, right? You're supposed to use a method to get what I think is the intended behavior of how computers do arithmetic, right? So this was very hard on me. Are you all seeing why Rust is a bad language yet? Or do these things seem reasonable to you? So it's not going to be on the final that you find this unreasonable, but I would feel better if you all agree with me that it's unreasonable. Okay, thank you. Okay. The program won't panic, but the variable will have a value probably wasn't what you're expecting. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. And there are 4 such methods: wrapping, checked, overflowing, and saturating. You will use the first 3 on the assignment this week. Or you will write it the way I wrote it, such that your code only works in release mode. Those are your 2 options. And once again, I would like to reiterate that your code only working in release mode, I think, is awesome. Okay? So you're definitely encouraged to seek out that particular form of artificial difficulty. Okay. This is the only slide I've added that isn't on number theory to this. I find having different numeric behavior in debug and release versions extremely questionable. I was talked down from having this opinion And then I designed all of the course materials this term, and it came up all the time. How many of you used overflowing add every single time you did an addition in SHA 256? SHA 512, yeah. You have to do that or it's not correct, right? I just wrote all my code with additions, and it works at high probability, right? But it always works in release mode. So who's to say that what I did was wrong, right? The Rust language designers say that my code contains errors, but I don't care what they think. This would have impacted F16 depending on how far you progressed through that assignment, right? I didn't expect us to get all the way to finishing implementing an F16 because that's not like a thing that makes sense to do. But basically, as soon as you started multiplying things together and they got too big, you should have been doing overflow checks on them, right? It will definitely come up on IX, the upcoming homework. So I don't know if this will be harder or easier. I think maybe it'll be easier because of wrapping, overflowing, and check being supported. Saturating seems pretty useful to me, or useless to me. So I have avoided using that. But in fact, saturation is what the floats do. The floats all saturate. So let's look at an example. I'm going to take this code, and we're just going to check to see what the biggest number we can store in an I32 is. It probably won't take that long. I think I can just copy paste this. That's probably fine, right? Do I have, what is bear? Openbear.png. Huh, wonder what that is.
Stock market? I don't know.
Yeah. It's, I don't know what it is. Okay. Wow, I completely stun locked myself. What we're doing? Okay, we're doing Rust. Okay. Numbers. Cargo new numbers. Okay. Okay. So what am I doing here? And I want you to know that I did not even remotely write this code right on the first try. I left out the mute tag. Here, we'll show what happens when I leave out mute. It's always good to write bad code. So I was like, hey, I'm going to create a variable n, and I'm not going to declare it as a constant. I'm going to use let, which is JavaScript for you're allowed to change the value of this thing, right? I'm going to let n, which is of type I32, which I shouldn't have to say. I think it's a I32 by default. I'm going to say that's equal to 0. And, well, n plus 1 is bigger than n. I'm going to add 1 to n. So I'm going to keep going until I hit the maximum. As soon as the next value is smaller than me, I'll know that I did a wraparound, and that means the value is incorrect. And then as soon as I get done, I'm going to leave that loop, and I'm going to debug n, and I'm going to debug I32 max. And I bet this will work no problem on the first try, so I'll just go ahead and cargo run it. And oh my gosh, I had to declare that thing as a mutable value. Okay, so that's no problem. That makes perfect sense. Just come in here. I'm going to get rid of these and see if it explodes. Okay, no problem. I'm definitely not about to take a ton of psychic damage here. Oh, that was really slow. Did y'all see how slow that was? I should time that. And I'm going to time it before I look at the output, because I'm probably going to be really upset if this takes a long time and then doesn't even output what I'm looking for, right? And I don't like to be upset. Oh, well, that took 3.25 seconds, which is pretty slow, but at least now I know the maximum value that an integer can hold. Oh, the horror! Oh no! Ah! Okay, the thread panicked without telling me anything because it said I attempted to add with overflow, which the Rust book said I didn't mean to do, but I told you all what I was doing, right? You're all my witnesses. The Rust book is wrong. We have proven it false. Okay. Not to worry, I have an ingenious plan. I'm just going to slap a release tag on here real quick. And not only will it run really, really fast, but it will also tell me what I want. So here we have it, Rust code that the essentially every single thing about it changes when you change the release flag. So I don't know. That seems sketchy to me. And that's okay. But what's going on here? I'm pretty sure what's happening is the overflow check that was supposed to occur at runtime is now occurring at compile time. Rust is saying, hey, this thing is going to overcomplote. It pre-computes the value, and it just outputs them directly. So I think that's what's going on here. I don't know. I'm not Rust. But also, if I run this again, it's even faster because it's not compiling. So more than half the time spent here was compilation. And then that goes away here. This is only just dumping text, right? And as we saw, we were about 3 times faster than this, just dumping text with Python. But this is much more heavyweight than that because Rust has to go and check to see if I've changed the file, do compile checks, look at the binaries, put them all together, run it, right? So this is actually very high performance even compared to Python, right? And Python also couldn't go this high numerically. So I don't know. That's kind of interesting. This is fast. Okay. Let's see how my performance compares versus at home. Pretty interesting. My laptop, why is that? So my laptop was half the speed at Python, but it was 200% on Python, it is 75% on Rust. So for some reason my laptop can run Rust dramatically faster than my desktop. I'm guessing that's because I'm running Rust inside of Windows Subsystem for Linux on my desktop, because at home your computer has to have Windows on it so you can play games on it, right? So we all understand that. Okay. And so this is 4.66 seconds at home or 3.253 seconds. I timed versus Python at 70 seconds to check to see if that value was in the natural numbers. And these are all about half the speed I got in the C programming language. I got this in about 2 seconds on the C programming language. Now, it is time for an in-class exercise. This is our favorite type of exercise because we don't have to do it outside of class, right? Given these values, 4.66 or 3.25, how long would it take to find the largest U64 value? Think pair share. I'm going to take advantage of this to go get some water because my voice is dying, and then I'm going to come back. But think about it, and then I will reason through how I calculated it, and we're not going to test it, okay? I'll be right back. I expect to hear yapping, okay? Are you yapping? You're not yapping.
Does talking to myself count?
No. That's assumed.
Exponentially double.
Oh, that's unsigned 64. I wonder how long we should put on that.
I think he said self-yapping doesn't count. So yeah. Was it just twice as long?
No, would be more than
Oh, like two.
because that's an exponential that you're doubling, not.
So what about just number squared, 3.2 squared? Because, I mean, does that make sense?
Maybe. I should know this. There's a specific thing for how exponents function. I just need to remember how it is. Is it that exponents multiply together? I think exponents multiply together.
Yeah, but yeah.
Okay, then yeah, it would. I think it would just be power 2. But I'm wondering if it being U64 versus or sine versus sine would have a large impact on it or not.
I mean, it's the same amount of cycles.
Yeah.
Still,
Well, it does have one bit less of things to get through. Which I guess. Okay, so technically it would be slightly over. I think it would be. I think it would be squared and then times 2.
and times 2.
because there's an additional bit, because it's unsigned versus unsigned. So you have an
Well, does
additional
that
bit
make
line,
sense?
you have to iterate it.
No, second, third.
Oh.
No, don't look it up.
Yeah, you're right. 'Cause it's
So that E is-
that makes sense.
Okay. So, a lot of people think when you're trying to do arithmetic, you should put it in the computer. But that's not true because running computers uses water. And I don't take water to operate. So, no problem. Yeah, it's true. I run exclusively off of Coca-Cola products. Okay.
That has water in it.
I'm pretty sure it doesn't. It's just corn syrup all the way down and carbonic acid. So, I need 4.66 seconds, I think, to calculate how many values. Well, it took this long to get to 2 to the 31. Okay. Inside a U64, the maximum value is 2 to the 64, which is 2 to the 33 times Bayer. Now, I happen to know about how much 2 to the 33 is because I just calculated it. So I think like, is it like 114 or something? 147, okay. This is about 2 to the 33, right? Or 2 to the 31, rather, right? And so that's no problem. So 2 to the 33 is about this much. It's just 4 times, right? So this much times that many. So it takes this many seconds. Well, this many seconds is about, I think that's how many seconds are in an hour. That's 60 squared, right? So we can just cancel that out. So it's this many hours, 10,000 hours, right? Am I close?
You're missing 3 zeros.
I'm missing 3 zeros. There's 3 over here?
No, all of them.
On all of them?
Yeah.
Yeah.
2, 1, 4, 7, 4, 8, 3, 6, 4, 8.
Okay. So there's 3 zeros here?
And on the
Yeah. Whatever. No one cares about these ones. That was me showing my work. See, this is why you use scientific notation, right? See, really, it's 2.147 times 10 to the 9th. I think. Okay. So that is 10 million hours, right? Well, that's not too bad. We can probably get this down to, what, days, right? So if we divide this by 24, I don't know, that's this many days. So that's 400,000 days. That's only 1,000 years. That's actually not that bad, right? This is much, much faster than checking Google Plex, right? Anyways, if you're ever curious to do something with numbers in a computer, use 8-bit integers so you don't do this by accident, right? Anything you want to check, you can check on an 8-bit value, right? I didn't realize this because I just did all of my math directly on 32-bit values for years and like waited the 10 seconds. And then at some point, computers had 64-bit values in them. And I was like, I bet I can use the default built-in integer type. And then after 1,000 years, I got my first answer back. But I only made that mistake once. I never waited the whole 1,000 years ever again. Okay. Ooh, this isn't updated from the C slides. That's a mistake. So these are supposed to be the UNs and the INs. As far as I know, I am not a mathematician. The unsigned ints and the signed ints used in C, Rust, and Python, and other languages are rings. A ring is a mathematical object. I'm not sure. I think it's a tuple that contains a set of values and then also some functions. It's a set that has addition and multiplication defined on it. I thought they were fields that is incorrect. Fields cannot divide 0 by something, but I actually can multiply two values together and get 0 inside my rings, because I can multiply 2 to the power of n divided by 2 times itself, and I will get 0 back. And I think I can successfully demonstrate this if I'm as clever as I think I am, which sometimes I am. So, let's see. I think if I do this, and I have to put that in a, oops. Does that go in a U8? I have a confession. I never remember where you're supposed to put the colon. But I can just cargo format this, and then Rust fixes it for me, so I don't have to remember. That's cool. Like, I like it when computers do things so that I don't have to, especially if the thing is remembering punctuation, right? For years, I wrote every single sentence without capitalization, commas, apostrophes, or periods. And that's why I'm so good at monkey type, right? Okay, so I bet this will run no problem. Oh, that was 15, not 16. What am I doing? Oh, my brain's exploding. Okay, no, we're fine. Okay, so this needs to be 1, and then we need to put in a 0. Okay. That seems fine. Ooh. Ooh, oh. Oh no. It's an overflow arithmetic operation. I probably didn't intend to do that. Oh, dang it, it's not allowing me. Okay. Wait, it didn't even allow it on a release? Could not compile numbers. Well, that's kind of sad. There's only one way to do this. I'm going to have to write my own multiplication function. Okay, so that's not too hard, right? Fun mul. I'm going to take an n, or no, I'm going to take an, we'll call it a, which is a U8, and b, which is a U8. No problem. What can I do? Well, now I can't multiply these things together, or that's going to trigger the overflow error, right? So what I'm going to do instead is I'm going to add a to itself b times, right? Easy. Okay. So for I in b, we'll create a mutable accumulator.
Oh, does it not care about the release flag due to being in a debug statement?
Oh, do you think that's what it is?
That might be what it is.
But I debugged the last ones, remember?
Yeah, no, never mind.
See? That's what I thought too. Does that look like a Rust for loop to anyone? Does that seem fine? I think that's allowed.
I've tried to do that before, and every time it yells at me that I don't include a 0.
I need to put a 0 there?
Maybe.
This is why Python's better than Rust. Oh, that even, I can't even pull that one off, saying that unironically. Okay, so we'll just say ACK. I'm sure I can put plus equal in here. It's supported by every language I'm aware of. So we'll just add a to that. And then what Big Rust wants you to do is just write ACK here, and I can't do it. I have to write a return statement. It's reflexive. Okay. Oh, wait, no, I'm still doing this. Okay.
So you didn't run it with the debug, or you didn't run it release.
There's other things I forgot, like to specify the return statement here. Okay. So I think this explodes. And is this one okay? There you go. Oh yeah. This is good. This is good. Your compiler should be upset when you don't use a variable, right? So you should have to clearly specify to it that you definitely mean to not use that variable using the underscore prefix. And this does not at all remind me of the fact that I thought they should have a specific naming scheme for data structures versus literals. but they don't have one. But they do have a specific naming scheme for when you don't use the variable. Okay, that's all. I'm fine. I'm not mad at Rust. Remember? Okay. Rust, good language. Okay. And that is exactly the behavior I'm looking for. When I multiply n by n times n, I can get to 0. That means there is a 0 divisor in U8, which means U8 is not a field. It is a ring. What is the difference? I don't know. Take an advanced math class. Okay. Rings have some goofy features. What are some of the goofy features, you might ask? Well, it is not necessarily the case that if A and B are elements of the field, that if I add them together, it's bigger than either of the two values. Here's an example. I'm going to take this. This is going to, loose quotes all over the place. You see this? Okay, I wasn't going to point it out, but so I think this is a loose quote. That's a loose backtick, right? And then so that must mean I double quote punctuated my file name. Very goofy. Okay, so let's go ahead and just grab this real quick. You have worked with arguments before, so I'm going to assume your familiarity with this. We're reading in numbers, we're parsing them and unwrapping them. Okay. Okay. Cargo run, let's see, I can probably put like 10 and 20 in here. Oh, no, I can't because that's hex. Can I put decimal 10 and 20 in here? No problem. A plus B is 30. Easy peasy, right? I bet this means I can add 100 to 200. Oh no. Oh, what happened? Oh, I attempted to add with an overflow. Wait, no, I have an idea. Okay? Everyone remain calm. I'm pretty sure I can just put a release tag here and then everything will work, right? Oh, it's 44. Of course it's 44. Why would it not be 44? The U8s can store up to 256. This thing adds up to 300. 256 plus 44 equals 300. Exactly working as intended, right? Super duper easy. So, that was nice. Here's how I'm expressing this mathematically. I'll write this on the board, but it's on the slides. So I'm going to say 100, this is all in decimal, plus 200, 3 lines. These 3 lines, this is LaTeX /equiv for an equivalent relationship. I do not pronounce this as equiv, I pronounce this as congruent. 100 plus 200 is congruent to 44. Congruent is a stronger form of equivalence. It is also correct to say 100 plus 200 is equivalent to 44. And then I specify, what do you mean equivalent to or congruent to? I mean with respect to the modularity of 2 to the 8th. So every time I go higher than 2 to the 8th, I subtract 2 to the 8th. Easy, right? And what this means is that 16, using x for times, 16 is equivalent to 0 mod 2 to the 8th, which means 0 divided by 16 is equivalent to 16 mod 2 to the 8th, which means 0 is divisible. Now, 0 is divisible in this numeric system. It is not divisible in U8s. So U8s differ from the number system in this case. This operation is true in U8. That's an 8, trust me. You can all tell by looking at it. This is different. When we refer to these, we refer to this as the integers divided by 2 to the 8th times the integers. And the reason for referring to them that way is beyond me at this time. I learned it in undergrad and I don't remember. It didn't seem interesting. And so I've tried to express that on this slide so you can see what it looks like. To my knowledge, I have never seen a mathematician put an expression here rather than a value. So I don't know if it is considered good form to say 2 to the 8th. To me, it is so unclear what 256 is and so clear what 2 to the 8th is, I have the preference to say 2 to the 8th. And in fact, this is preserved in the computing sciences where we say U8, we do not say U256, right? Only the power is relevant to us. Okay, and we can verify the same features using our favorite programming language, not Haskell, but in fact Python. In practice, you may at various times in your life want to consult what the maximum values are. You may also memorize them. I have seen I32 and U32 max so many times. As soon as I see them, I know what they are. U64 max has so many digits, I have never once recognized it. I'm going to print it out right now, and I'm going to be shocked by what it is. Okay. U32 max. No, that's the 32. I was checking 64. Okay. Yeah, I don't know. That number doesn't mean anything to me. It's too long. It's like if someone started telling me their phone number and they were like 1, I'd be like, all right, got it. 844, I'm like, I'm locked in. 674, like, I'm totally fine. 4073, I'm like, got it. And then they keep going, I'm cooked, right? I can only remember 10 decimal digits.
I think there's like memory falls off around 7%.
That can't be right. I have perfect memory. I've remembered everything that's ever happened to me. I don't remember anything that I forgot. There we go. We got it. We brought it back. Okay. Can I hear it for tautologies? Yeah. All right. Okay. That wasn't very enthusiastic. But that's okay. Okay. Here's our problem statement. When you're using good old GitHub, we all love GitHub, don't we? One of our favorite Microsoft products, now an AI company. We're definitely not at all getting nervous that we're going to be redeveloping all of our course materials to not use GitHub next year, right? No one's concerned about that. I'm working on a grant to switch to GitLab, and I was like, wow, I use Git for everything. Okay, so when GitHub tells you to generate an SSH key to access their website, they recommend, if you're using RSA, which we're not using RSA anymore, but the other example doesn't specify its bit size, so I'm still using it as the motivating example here. You're saying, hey, you crazy kids better give me a key of at least 4,096 bits. And I was like, wow. That's like half a kilobyte, right? That's so much. You could probably store a pretty good MIDI file in that much information, right? Our ancestors probably implemented the entirety of Super Mario using just those bits, right? And so we should get pretty stressed out by that 4096 because that's a lot bigger than our biggest Rust integer type, the U128, right? So that's probably going to be a problem for someone starting around like Friday, right? Okay, so modern security recommendations for RSA are for 496-bit keys, and 2048 is generally accepted. And then there's people that use whatever the 3K one is in there, which is 1.5 times 2048. You probably have this utility on your device, and it's probably going to default to this cryptographic system, which is the one I'm going to teach you. But you can also specify other cryptographic systems, such as whatever this thing is. Can I actually select this? Okay. This is the link to the docs. That's why it's hard to click on. It's like, oh, I can generate a public-private RSA key pair, right? So, did you notice that that didn't run instantly? And I'm not going to save this right now because I don't really want to be generating private keys in class, but, you know, you can do it. So this is something that is probably on your device. Does anyone want to check and see if this is definitely on their device somewhere? Any brave heroes? No? You don't have it? I knew you wouldn't. Okay. It's always someone. It's always someone in the front row that claims to not have it too. That's what I've noticed. Okay. So anyways, I've taught you about finite sets and rings, and so I have a confession. You might have realized this about me by now. I really like programming language and number theory, and so we are 1/4 of the way through the class material, and I've been talking for over an hour. This is not at all a cause for concern. Okay, so soon we will implement key generation. What do I mean by soon? I mean once you're done with the integers, right? I have my responsibility, which is to prepare to teach you that material. You have your responsibility, which is to implement the integers. I already implemented the integers. I did it this week. So we're getting there. And we'll talk about what key generation is once we're ready to generate our keys. But for now, we need big numbers. And so we're going to use U64s. You are not required to use U64s, and in fact, my library works just fine if you use U8s, U16s, or U32s in it. It's just slower. And you can also use U128s. So we're going to use probably U64s to model the infinite values. To motivate how we're going to do this, I'm going to yoink an example from data science. Can I hear it for data science, folks? We do love data science, right? Data science not really helping computer science beat the allegations that if you have science in your name, you're not a science, right? It's like, we could have kept it chill, right? You could have been called data analytics, right? Everyone agrees it's analytics, right? Okay. So we had a data set for which we determined a mean height in inches. When did I do this? I don't know. It was like in a machine learning class I taught or something, right? And I found it very interesting because it had this numerical feature. Python 3 C print, what is it? 69.3 mod 12. So I would have really thought this was going to come back as 9.3, but I'm not at all just coming up with every single example I can of why floats are garbage. So I thought I would leave this in, right? Anyways, this is average self-reported height of self-identified men in some data set someone used for something. And it's always fun to ask people how tall they are and what their gender is at the same time, because then you can compare it to the population rate and there's no correlation, right? So like I think I'm like either 4'2" or like 6'9". I don't ever remember which one, right? But I'm definitely not 5'10". That's average, and like I'm special, right? So like, okay. Since this was about people saying they're taller than they say they are, I decided I would pick my favorite WNBA star, who I didn't know how tall this person was, but Ajay Wilson is 6'4". I have no idea how tall that is because it's not in metric, so I don't know if that's tall or not, right? So in order to figure out how much taller this is than 5 feet 9.3 inches, which might be how tall I am. How tall do I look? Do I look like I'm 5'9.3"? I bet I'm average. Okay, we can convert that to non-integer inches, but as soon as you start using integers, do you really trust your computer anymore? I wouldn't. I would never use my computer for anything that isn't an integer, right? So I'm not going to. Instead, I'm going to perform long subtraction. And do you all remember learning subtraction in like elementary school? Because I do. That's when I peaked. That's not true. I peaked in middle school. But I was on my way to peaking in elementary school. And so I think the way that you do long subtraction is you like line up the digits like this, and then you subtract down the columns. So how am I going to do this? Well, I'm going to take 0, and I'm going to subtract 3 from it. And what was that? What was that, Rust? You thought I didn't intend to wrap around my results? No, I did this in elementary school. 0 minus 3 is 7. And you carry a 1, right? So I just add the carry bit in there, right? Take that, Rust. Elementary schoolers are smarter than you. Okay, and I'm not mad. Okay, don't put in the course of vowels, I'm mad. Okay, so what are we going to do now? Well, we need to subtract this 9 from 4, and we also need to subtract 1 from 4. And this is going to get really, really fun because we're doing wrapping underflow subtraction in base 12, right? Everyone always tried to trick you into thinking you're really going to have to use base 10, right? And then I started making you do hexadecimal and binary. Now I'm making you do base 12, okay, right? So if I take 4 and I subtract 9 from it, and it's in base 12, well, I'm going to take 4 off that 9, and I'm going to have 5 left. Then I'm going to subtract 5 from that. And so that 5 is going to come off of 12, which means I'm going to get 7 back. And then I'm going to take off the 1 additional carry bit, and I'm going to get 6 back. So I think this is going to say 6, but I don't actually know. Were you all able to follow along as I did that verbally? Or are you completely sketched out? Okay, it was 6. What a relief. How do we know that? Well, you can add it back up. So 6 plus 1 plus 9 that's 16. It's base 12, so we take the 12 off. There's 4 left. There's the 4. Boom. Easy, right? So fun. I love doing long subtraction in base 12. Quote me. That's do you want? Let's do a repeat after me. Okay. I love doing long subtraction in base 12.
I love doing long subtraction in base 12.
Wow, I've never heard anyone else say that before. It's almost like you were prompted. Okay. Remember how I mentioned there was a carry there? So we need to update this carry bit to a 1, but we got rid of that carry bit. I shouldn't be calling them bits. I should be calling them digits. It would be more proper to refer to them as digits in this case. And then we're going to carry out our remaining subtraction. This one's not that bad. This is 6 minus 5 minus 1. That's exactly 0. Right, so that's easy. And it's non-modular because we can have an arbitrary number of feet. You can be as many feet tall as you want. It's not like inches. When you go over 12 inches, you get in trouble and you have to turn into feet. Feet can be as tall as they want. Now, I don't know if this is true, I've never heard someone's height reported in decimal, like leagues or miles or something, right? But I'm sure that's allowed, you know? So I'm saying non-modular, I'm saying feet has no max. So 6.7 is how much taller. Okay. So there's tall people. They walk amongst us. I actually don't think Aja Wilson walks amongst us. I believe she lives in Las Vegas. So that's like maybe like if you went to Burning Man or something, right? So the same way we solved that problem, we can solve the problem of doing arbitrary precision mathematics just using U64s and potentially using a sign bit or not. So now that I've taught you how to do this, you can do arithmetic correctly, which, again, I would like to point out Python cannot do. This is wrong. That is just wrong. There's no way to argue this is correct. You can be like, oh, it's trying. No, it's not, right? It's a computer. It doesn't try things, right? It deterministically produces wrong results 100% of the time. It cannot, grow, learn, or change, right? That's its intended behavior. So it cannot do arithmetic, but we can. So we're going to do so. There's a frequently asked question I always get when I teach this. Can we use this to add numbers bigger than 2 to the n using adds over at most n bits at a time? Yes, you can. You can do anything you want. You're so powerful, right? All you have to do is change the modularity, and you're set. Because set. It's also a sports reference because bump, set, spike, right? So that's two different types of set on the same slides. Okay, can you do this for more than 3 units? So I did decimal inches, inches, and feet. Yeah, you can do it for as many as you want. The reason I used a 3 example is because I wanted there to be carries twice, so you could see how you would initialize and terminate this sort of for loop over digits. And so that's arbitrary and high precision integers. And now I'm going to talk about arithmetic operations for 10 minutes, and then I've given this, this complex of lectures in a bunch of classes. And I've never gotten a really strong sense for how long it takes, but I've never finished it in one class. I think we will still do the planned lab on Wednesday, but I might start with lecture. I'm going to go home and look at what we missed and what you're going to work on, and I'm going to look at my solutions to see what you need to know. I will deliver all of this content at some point, but I don't know. I feel like I'm kind of going as fast as reasonable already because I was doing, again, modular-based carry subtraction-based 12, which you can just only do that so fast. So I'm going to tease the arithmetic operations, and that's going to be pretty good for now. So I'm going to claim that it is relatively easy to do infinite precision addition and subtraction. I think if I gave you no instruction on it and just told you to do it, you would figure it out. And I especially think that's true if you did addition first, then tried to do subtraction. I think if you started with subtraction, you might have some weird things come up. So I'm going to say this is easy for some value of easy. The way you do it is you cut up the big number into chunks. It is quite common, and I didn't know this, many people that implement arbitrary precision integer libraries actually do so base 10. They figure out the biggest base 10 multiple that can fit in some integer size. So in a 32-bit, it's 10 to the 9th. I have written somewhere. So you just do everything base 10. That also makes it way easier to print these out. I'm extremely not going to let you do that. I'm making you do hexadecimal because that's for cowards. But I guess if I never found out, you still have to print out in hexadecimal. So how you do that? You break it into chunks, and the chunks are just like whatever size your underlying hardware works on. Maybe you should break it into chunks of size Boolean. Maybe that'd be sick, right? That could be really cool. So you just think about it, right? But if you don't want to break it into chunks of size Boolean, that's fine. You can use U64s. You can use U28s. Then you just add and subtract within the chunks, and then the only thing you have to do is distribute carry bits. So how do I do this? I do this sequentially. I start at the least significant bit, and I work my way up, taking the carries with me all the way. I also still call them carries for subtraction. I think there might be a different name when you're subtracting. That's all you have to do. It's a simple for loop operation, and it is, I claim, identical to digit-based addition, long addition or long subtraction. You can think of these, and I actually do encourage thinking of this way. You can think of U8s as digits in base 256 arithmetic. I know you can think about bases because I gave you a bunch of midterms on them. See, I've been tricking you for a long time. I'm sorry, right? I know you can think about bases because you did it on the midterm, right? So you can always just think, we just imagine there's 256 printing characters you can use. You can just print out the numbers in base 256 and you can look at them. Or worst case, you can just think FF is one digit, right? And 10 is one digit. I can't even type. Okay. Wait, is it a 0? I've never thought about it before, right? You can just say, that's just one digit, right? Okay. Now, this is not a math class, right? But I'm going to get into a little bit of advanced math, and I'm going to ask you to do multiplication, okay? I know, right? I see your face, right? The horror. I really try to avoid doing multiplication, right? Especially when I can write a perfectly good for loop and just do a bunch of additions, right? But I am going to make you do multiplication. I'm not going to make you do division because we've still never found someone that can do it. But as soon as we figure out an easy way to do it, I'll teach you that, and then I'll make you do it, right? Division and modulo, it helps that it's only one thing because you compute the remainder and the divisor at the same time, so it's only one operation. But it was pretty rough. Okay, so I broke this out by looking at how many person hours I was destroying per week last year, which is this many. I don't know that all of you are ever told about the credit hour policy at this university, but it actually might be relevant to you. For every 1 hour of in-class instruction, I am allowed to assign 2 to 3 hours of homework, apparently. Have you all heard this before?
Every single instructor has said this.
That's good. Now, I think the MS level people actually have a slightly different arrangement. But anyways, my assessment is I get 6 to 9 hours per week out of all of you for 15 and a half weeks. And then at the MS level classes, those are 14-week semesters, and they have to be 14 weeks because, if you have one Monday off, everything explodes, right? So they meet 4 hours per week instead of 3, and they have a fewer weeks. So I get 9 to 12 hours per week out of them. So let's figure out how many person hours that is. It's easy. I'm going to multiply the 14 MS level people times the 12 hours I get per week times the 14 weeks in the semester. And I'm going to multiply the last term I had the 34 BS level students times 9 hours a week times 15 and a half weeks per semester. This was beyond the limit of my cognitive abilities to just do this in one atomic operation. And it may be the case for you as well. But it doesn't matter that I can't do it in a single atomic operation because I'm able to describe the algorithm to do it, and I'm still able to push through and determine the mathematical result the same way I did this, right? So, first I'm going to try and get down to a smaller number of digits. 14 times 12 is not that bad. It's 140 plus 28, or it is the number of weeks in a year, or hours in a week. So that is 168. 9 times 150, or 15.5 is also not that bad, right? Multiplying by 9 is easy, so that's 139.5. From there, all I have to do is I have to multiply 34 times 139.5, and this is the hours of undergraduate homework that I collected last term. Slightly lower this term. I think there's 27 of you, and there's like 12 people here today, so I don't know what's going on with that. Is everyone sick? Or are the vibes just bad? Sick? Maybe? Okay. Ill. Do people still say ill? Yeah. Okay. Unfortunately, I think we could do this mentally pretty easily, but I'm going to follow through and just express this digit-wise. So I want to do a multiplication. I'm going to break this out essentially as a matrix. I'm going to compute the products being the single atomic term of multiplication, over all of the single-digit factors. Each one of these operations is quite simple, right? It can take place in a very small amount of time. There is one problem, and this problem should freak you out, which is that I multiplied things that were 1 digit in size together, and I got a bunch of products back that were 2 digits in size. This is terrifying, because it means if your working size is a U64, and you're multiplying U64 things together and thinking of their digits, you actually need 128 bits of precision to capture that. The way I solved this, and I do have a working reference implementation of this, is I did everything with 32-bit values. I loaded the 32-bit values into 64-bit values, multiplied them together, cut the 64-bit values in half, and I kept doing that iteratively. So those aren't single digit, and they aren't of the same significance. So in addition to perhaps having to break this up into 32 or 64 or 16 or 128 or whatever, you're going to have to use different sizes of numbers for products as you are for factors. You're also going to have to keep track of the comparative significance of each value. You're going to have to know what power of 2 or 10 or whatever they're multiplied by, which will be easy for you because you've already implemented floating point values. So we can also include significance, and then these operations are still quite easy. But you can't really do this with the computer. You're going to have to cheat somehow. Once you've done this operation, it is simple enough matter to add all of these up. These are simple sums. You can do this as a vector sum. I just wrote out the whole thing here so you can see it. You can express this in varying ways. I very strongly think of these as polynomials over some base. And that gets me to this slide, which I really wanted to show you today for the psychic damage. So anyways, this is where we'll start next time. But I think it's obvious what's going on here, so I don't need to worry about it too much. Thank you all for being good sports today. See you Wednesday. Oh, don't get sick. Sleep enough, eat enough, hydrated. Come on, you gotta stay hydrated.
Only that one, though.
Okay, if I only got one, I'll take that one. Okay.